Let me begin by thanking Rama and Shravan for inviting me to give this talk. Also, let me begin by expressing my congratulations and best wishes to Srinivasan for the years and days ahead. Unlike the previous speakers and most who will follow me, I don't know him personally well enough, but just to say that he has influenced and provoked many of us most of us working in this field. And the reason I'm going to talk about this is probably, hopefully, to continue in that tradition of provoking and on a problem on which Srini has worked a lot, which has to do with intermittency in turbulent flows. So I'll also take the advantage that there are 3 days more to this meeting, so I'll probably won't spend a lot of time on the newer results, but just to set up this problem, since it's sort of takes a little departure from the usual Navier-Stokes equations and turbulence that we are familiar with. Okay, so with that background, let me try to sort of encapsulate in a slide all that Rahul was talking about yesterday, which has to do with the problem of turbulence. And as was mentioned yesterday, the sort of framework at least, to understand turbulence is due to Kolmogorov. And one of the consequences of that is that the energy spectrum goes k minus 5/3. And sort of a more immediate consequence for this talk is that you have scaling exponents of equal time structure functions, which is you take the velocity differences across a scale r, which is suitable in some sense, and then you take its moments and you find that, if you follow the prescription of Kolmogorov, you sort of end up with scaling exponents which are linear in P. However, we know that this is not true, and so here's a sort of figure taken from Frisch's book, where we see that actual measurements of these scaling exponents seem to depart quite significantly for higher orders when you actually measure these guys. And what sort of there is a general consensus, I think, that zeta p is not equal to p by 3, and that these exponents are actually multiscaled in some sense. And what goes wrong in this picture, one of the things which certainly goes wrong, has to do with what's known as intermittency, a word which has been used frequently in the last day and a half. So let's try to understand a little more about what are these fingerprints of turbulence, and this will set the stage for the model that we are proposing, or we have proposed in the past, which seems to sort of suggest some implications for these. So here are probably, in the non-equilibrium stationary states, here are probably 3 of the most ubiquitous fingerprints of turbulent flows, and they have to do with the chaoticity of the flow. They have to do with the fact that the system is irreversible. And what will really be the bulk of this talk has to do with the fact that intermittency seems to crop up everywhere. So for example, if you were to look at statistics of acceleration, if you were to measure Lagrangian trajectories and try to look at exponents associated with these Lagrangian measurements, wherever you look, you end up having corrections because of intermittency effects. And there's another thing that I'd also like to highlight is that recently Jeremy and his team sort of showed that this is not strictly, all the results that we've had so far have largely been about fluid turbulence, but when you actually look at particles or droplets in turbulent flows, the effect of intermittency shows up in intercollision times, or how aggregates grow in such problems. So intermittency seems to be everywhere, and one of the, historically there have been ways to understand this signature of turbulence, and these sort of go back to models which have been based on velocity, models which have been based on dissipation, even simpler cascade models like the shell model, and I mentioned this because I'm going to speak a little about this since there were some questions yesterday at the poster session. And all these models are in some sense a rationalization, a formalism to rationalize observations that we see in experiments and simulations of the Navier-Stokes equation. So recently, I mean not so recent anymore, with Uriel, Anna, and Itamar, we developed this idea of turbulence in non-integer dimensions, where some of these fingerprints seem to disappear. And in this talk, what I'm at least going to try and emphasize is what the model is, without sort of being too grandiose or advertising about its virtues. So try to sort of convince that there is a model, and we would like to sort of try to understand how far this model can be pushed. Okay, so before we get there and try to see the implications of this model, so let me try to describe this model a little clearly. So what we begin with is the 2- or 3-dimensional incompressible Navier-Stokes equation, which all of you have seen in the last couple of days. But what we do is we now evolve the Navier-Stokes equation on a prescribed set of quenched Fourier modes. So what we essentially do is we take the Navier-Stokes equation, and imagine you're solving it pseudospectrally, as many of us do, and then you use a Galerkin projection to actually solve it on a subset of Fourier modes. So you introduce a quenched disorder in your Fourier lattice. So once you set up this rule such that your velocity, and you pick out this factor gamma, which can be 1 or 0. So for example, in normal solutions of Navier-Stokes, this is always 1. So all modes exist. But now you say that either in a homogeneous way, so with a given probability as you go to each kx, ky, kz vertex, you either kill it or you keep it with a certain probability. Or you can do it in a more scale invariant way, where this probability depends on your scale k. So how far are you from the origin? And we'll see that there are sort of interesting differences when you adopt either of these strategies. So a natural question, of course, and it's a very valid question, is why bother? So let me try to sort of answer that question a little before we start playing with this weird model. So why bother? So one of the reasons we sort of stumbled upon this is in trying to understand what is the interplay between non-equilibrium and equilibrium solutions of the Navier-Stokes equation. So what do I mean by that? So if I take the full PDE with infinite degrees of freedom, or if I take the inviscid version of the same equation, what are the consequences when you do either of the two games? So we know that you have the standard conservation laws, which have to do with energy and entropy in 2D, and in 3D, this has to do with energy. So if you were strictly in the Navier-Stokes business, where, again, to sort of fix ideas, gamma k will be 1 for all values of k, you'd end up either in 2D with the dual cascade picture of Crichton and others, or in 3D, you end up with the k minus 5/3 scaling. However, if you look at the Galerkin truncated inviscid versions of this equation, what you end up is with equipartition spectra. So this plot is actually from Mark's paper, so he's in the audience, where you show that the energy spectra actually follows k squared, or k to the power d minus 1, purely from dimensional reasons. However, if you have a different conservation law, namely entropy, you'll end up with a spectrum which is kd minus 3. This is for the 3D Euler that Mark and his collaborators worked on, and so you end up with a scaling which is k squared. All right. So the question that one can ask is, so we know that k squared looks very different from k minus 5/3, right? So why in the world should we be bothered about trying to even look at equipartition spectra, because they're so different from everything that you see in experiments and measurements? So you can ask yourself the question, could there be special dimensions where this spectra coincides with the Kolmogorov spectrum? And if you can see these dimensions, then does it tell us a little more about what's going on in the full Navier-Stokes equation? Okay, so the question then is, are there special dimensions where this equipartition spectra coincides with Kolmogorov results? So imagine that there's a dimension d, and if you're thinking of just the energy conservation, then you end up with a critical dimension which is minus 2/3. That's completely crazy. It's hard to imagine what sense you can make of dimension minus 2/3. However, if you're thinking of the entropy conservation law, which 2D Navier-Stokes guarantees you, you end up with a critical dimension 4/3, a little less than 2, and that doesn't seem too bad. So are these sort of theoretical arguments, and I should emphasize that there was a prediction by Lvov, Pomyalov, and Prokatya before our work. So the question is it possible to actually see these numerically, these dimensions, and then what can we do about that? So what one can do is one can begin with the 2D Navier-Stokes equation. Since it's a Galerkin projection, all the invariances remain true, so you have no problem in actually destroying the invariances. And when you actually do a simulation by decimating from 2 dimension in a fractal way, so you're reducing the dimension of the system without destroying all its conservation laws, you end up slowly getting a fluxus solution. So here, for example, we are looking at the energy flux, and that seems to go to 0, which is sort of masked by, this might be the best place to look at it. So for example, if you're looking at the Plato in the energy spectrum, essentially the flux, and then you start going down from d equal to 2 to the critical dimension, you see that the flux tends to vanish. And that has consequences for what happens to the Kolmogorov constant, etc., in turbulence. Okay, so that's the sort of digression or the background by which one stumbled upon this model. So I wanted to sort of lay it out so that I don't start decimating Navier-Stokes immediately without a context as to why we started playing this game in the first place. And also, as I mentioned in the beginning, I should like to emphasize that you can play the same game and have an understanding of what equilibrium solutions are in a more simpler model of turbulence, namely the shell models, where you can tune just one parameter, here P, and have a rich phase diagram of solutions which go both for the sort of cascade-like solutions with which we are more familiar with, as well as equilibrium solutions with standard scaling laws. So in a sense, and I won't be sort of discussing this a lot, but I just wanted to sort of emphasize this, is that apart from the usual DNS games that one plays, it's also useful to look at simpler models, dynamical system models, such as the shell model, which are ideal to actually investigate these questions of the interplay between equilibrium and cascade solutions. And actually, when you start doing that and you measure back to zeta p's, since we began with zeta p's, you sort of end up measuring these scaling exponents, which can either be those corresponding to equilibrium solutions in the same model by just tuning one parameter, or you can end up with a system where you have more turbulent-like solutions with the right exponents, with the number 3 appearing in the denominator everywhere. All right? And the shell model is very useful because you also tend to see, so for example, here what we did was we measured what's known as the equal time structure function for different values of the single parameter B, which again keeps all the conservation laws intact. And then you see that you end up in the structure function with different scaling regimes. You either get equipartition results, and here is a plot of the exponents as a function of B. You can either get exponents which are 0, which correspond in the shell model world to equipartition, equilibrium solutions, or you end up asymptotically as B approaches certain critical value of -2, you asymptotically end up with more turbulent solutions. All right? And you can sort of look at this picture even when you're studying the dynamics of these models, and you look at out-of-time correlators, and there, again, the picture is very clear, with a more interesting crossover as a function of this single parameter between equilibrium solutions and turbulent cascade-like solutions. So this is, just to highlight that this feature of equilibrium versus non-equilibrium is not just confined to decimated Navier-Stokes, but it shows up, as we sort of discovered very recently, it shows up in cascade models, such as the shell model. All right, so with that preamble, let's go back to the three-dimensional Navier-Stokes turbulence and try to see what this protocol tells us a little more about the peculiar features of the Navier-Stokes, which have to do with its chaoticity, irreversibility, and intermittency. Just to remind ourselves, we take the full three-dimensional Navier-Stokes, we project it on a quenched lattice, and then we end up with the decimated Navier-Stokes, where you have weaned out some degrees of freedom and then solved them. So the first thing which sort of tells us that we are in a good space is if you measure the energy spectrum. So remember, there are two ways one can sort of kill these modes, and they could be fractal, so where the probability of actually survival or non-survival depends on how far you're in K space, so that's self-similar, or you could do it in a homogeneous way, where you assign a certain probability which has no K dependence. So the good news is that the energy spectrum seems to be exactly what Kolmogorov would have given us. So we have a model where we haven't yet thrown out the baby and the bathwater, all right? So we have, except a little correction when you have a self-similar term, but that's a little technical, so we can discuss that later. Okay, so what happens to these small-scale fluctuations, which people assume have most to do with intermittency and turbulence? So this is from the work of, you see the names there, and Shiva is also in the auto. The three-dimensional Navier-Stokes equation down to degrees of freedom which were less than 1, they saw that there was an immediate suppression of small-scale turbulence. So for example, when you measure the PDF of the vorticity along any one direction, it quickly loses its fat tails and starts becoming Gaussian. So you're ending up with a system where you have everything which is turbulent, but signals are Gaussian. So that's good from a theoretical point of view, because it sort of gives you hope that you can do something about these systems perturbatively, all right? So if you then go ahead and measure this departure from non-Gaussian behavior by calculating the kurtosis of the vorticity field, you see that as soon as you decimate just a little, about 0.05, so 5% of the modes are not, of the triadic interactions are not contributing, you see a singular jump to the value 3. So in full Navier-Stokes, you have kurtosis which is of the order of 10. The minute you have sort of killed off some of these interactions, you end up with an Eulerian intermittency which is completely suppressed, and you end up with values of 3. What happens in the Lagrangian framework is even more dramatic. So let me define this a little. So just like the Eulerian structure function where you took velocity differences across scale R, within the Lagrangian framework, you can construct an analogous correlation function which has to do with following tracer trajectories and taking velocity differences across a time lag tau, all right? So when you do that, and suppose you were to measure the local slopes in an extended self-similarity way, so this black curve is the one that we are very familiar with from all earlier measurements of Lagrangian structure functions. The mid and alpha here, sort of alpha equal to 1 means it's Navier-Stokes 3D. Alpha less than 1 means that you've sort of weaned out degrees of freedom. The minute you go less than 1, the curve changes. And this is sort of most dramatic, again, if, for example, you look at the kurtosis of the Lagrangian structure function, and although in the Navier-Stokes, this is sort of order 50, order 60, depending on how high your Reynolds number and your measurements are, again, the minute you sort of decimate a little, and that's somewhere here, you end up with values very close to 3. So the basic message so far is take the Navier-Stokes equation, integrate out the degrees of freedom if you were trying to do it analytically. Numerically, you solve the equation on a quenched lattice. And the minute you do that, although all symmetries and invariances of turbulence that we are familiar with persist, but signals start to become Gaussian. And that's really strange, all right? So this is what I meant by saying that here's a way to actually kill intermittency in the sense. So I should also sort of point out, I won't be discussing this much, is that a lot of these results can be rigorously shown, was rigorously shown by some of us in this paper for the Burger's equation, where the basic message is the same, where you see exactly the same features, but there you're able to compute theoretically much better the different tails in the distribution function, and you're able to sort of see this see this phenomena analytically much better. The surprise for us was when we started to evaluate the bridge relation which connect the Eulerian and the Lagrangian exponents. Again, another observation which suggests that this decimation protocol is really harmless. So you can use the prescription, for example, in Schmidt's paper, and construct the bridge relations between these two set of exponents, and you see that the bridge relations are valid, even under decimation, even under the fact that signals turn Gaussian. So they do it in a way in both the Eulerian and the Lagrangian framework so as to preserve these relationship between the two sets of exponents. Okay, so in the last sort of 5 minutes that I have, I'm going to also talk about another aspect. So I began with these fingerprints of turbulent flows, which had to do with intermittency and irreversibility. So in the last 5 minutes, I'm sort of going to talk a little about what we are seeing, which is a very puzzling result as to what this decimation does to the reversibility of the flow. All right? So just quickly, the way we are going to analyze in this talk is to make use of Lagrangian traces in the flow and actually look at the Lyapunov exponents and try to see if they're telling us something bizarre about these systems. So let me come here. So for example, if one were to look at the middle Lyapunov exponent, which often is an indication of the reversibility in the flow, and one were to plot it as a function of how many degrees of freedom you have killed, you see a certain emergent reversibility appear in the flow. It doesn't go to 0. Lambda 2 being exactly 0 would mean that it's reversible, but you do see a sharp drop from the three-dimensional value of about 0.25, suitably sort of scaled, to something which is at least a factor of 5 smaller. And this emergence of a reversibility in the decimated dynamics is something which is rather striking. I mean, there are other Eulerian measurements of this which sort of suggest the same, for which we have no understanding as to why this is happening in our system. So I will end with certain, perspective and conclusions, and this has to, and this is really sort of, in some sense, the aim of this talk, which is the following. So what we now know for sure, using this method, is there is a critical dimension in turbulence, in the sense that you end up with fluxless solutions. So it's critical in the sense that equilibrium statistical mechanics Gibbsian distributions are coincident with the Kolmogorov picture, right? So what one is now, and that's numerically attainable, and what we are now trying to understand is having such a critical dimension, which is not too far away from physically relevant 2 dimensions, could we use perturbative techniques on these Gaussian fields to actually understand more physically relevant turbulence better? 4/3 isn't that far from 2, right? What is clear, and I think we are willing to stick our neck out on this, is that intermittency is indeed suppressed the minute you kill off some triadic interactions, and you can do that randomly, or you can do it in a scale invariant way. The message is the same. So it's a problem where keeping all conservation laws, all symmetries of the Navier-Stokes equation, we have a way to get rid of intermittency. And having got rid of intermittency, the question is, what should we do about it? All right? So maybe I'll say a couple of things about that. The other thing which is sort of ties into the second point is that the Berger's equation lends itself to certain rigorous results, which are consistent with the numerical observations and the numerical experiments that we've done for the Navier-Stokes equation. And what's really surprising right now, and that's sort of not written up, is the appearance of an emergent reversibility in the problem, for which we have zero understanding as to what the triads are doing when you wean out a subset of them, the fact that there is a certain emergent reversibility. What's the sort of perspective for this? the perspective, again, is what I mentioned, is around the critical dimension. Are there ways to obtain exact results for D equal to 2 turbulence? And an allied question, and there has been some progress on this, is if you're looking at closure models such as the EDQNM, can you predict similar Gaussian features from models such as the EDQNM? Because you can use a probabilistic argument to construct your closure models, exactly how you construct your Fourier lattice to gain some understanding for the 2-point functions. And now, especially in Luca's group, people are using these ideas to push in modeling, because at the end of the day, especially when you are scaling with K, you are really killing more small-scale structures than large-scale structures. And then for large models such as the large eddy simulations, could these be used as a better subgrid model to actually mimic the small-scale structures? And the last thing I wanted to emphasize is that the numerical approach to actually solving PDEs in non-integer dimensions seems to be a very generic one, the way, at least the way we set up the problem. And so it remains to be seen, for example, how does this tie up with other problems in hydrodynamics, for example, in MHD turbulence and dynamo, whether you can use these ideas and gain an understanding about dynamo growth, especially small-scale dynamos, using these decimation ideas. So I've eaten into my discussion time, so I'll stop here. And thank you.
So we have good 10 minutes for discussion. 10 minutes for discussion. It's 30 minutes plus 10 minutes for discussion. So,
is there a temporal analog of what you're saying? That is, instead of just making these choices in space, could I make it in time somehow?
I have not thought about this, but since you ask, I don't see a way. I mean, there is one way you can make it in time, which is you can take your signal. So you begin with the Navier-Stokes, the full Navier-Stokes, take your signal at discrete times, and then filter it through this lattice. Is that what you're saying?
Well, something like that.
So this is what. These people did. Luca Shiva, who's here, where they looked at this kurtosis. So DM stands for things which are dynamically evolving, so the problem that I described. And SM is solution of the Navier-Stokes, but then at discrete time intervals, they filtered it through such quench lattices. And it does seem from their data that the effect of this decimation is delayed as a function of how far you're in dimension. So you're still reasonably intermittent up to a much higher dimension, up to a much lower dimension, 3 minus d, and then you end up getting to a kurtosis value of 3.
Yeah, I mean, as somebody much more versed with experiments than with anything else, is there some lesson I could learn from here, or it's only a conceptual thing for?
I think at this moment it's still a conceptual thing. Yes, I would be very surprised how to extend this to. I mean, the only thing one can do from an experimental data is exactly what I described here, where you take the data and you filter it post facto. I've forgotten what SM and DM. I mean, M stands for mask, and S and D, I forget what they say. Static and dynamic. Okay. So in an experiment, one can certainly do this. You have the data, and then you filter it. That's right. Yeah. And assume that the experiment sort of replicates the 3D Navier-Stokes quite well. Yeah.
So I think this finding that it takes so little to destroy intermittency, essentially, you just take a few of the Fourier modes out, is very dramatic. I wonder whether it also could mean simply that the Fourier modes that you're using as basis functions are simply very bad represent intermittency. And I wonder whether this decimation idea, in a fractal sense, meaning that you don't produce new length scales, could perhaps also be replicated with basis functions that are perhaps spatially more localized, such as, I don't know, vorticity in wavelet space. And that's
right. So you separate the it's not been tried, but that's something that some of us have thought about. But just to sort of quickly, since you raised the point, what I should have emphasized again is this. So for example, in the burgers, and that's the point you raised, that you need just to decimate a little, so it's really singular, is in the burgers, this is clear. So you start with 1D, and the minute you decimate just a little, so you go down to dimensions about 0.99, I think, and then you quickly go to a completely different regime. So it's really like a phase transition in that sense, so like a first-order transition.
This is also in a Fourier sense, this
in a Fourier sense. So the other point that I didn't stress enough is that what we are sort of really hoping is intermittency signatures purely in the Fourier space to actually settle this issue. Because here there is a certain crosstalk where we go back and forth. Also, you can argue that if you're thinking of the Lagrangian system, how valid is the fact that dx dt equal to u once you sort of decimate, and there could be sort of conceptual issues there as well. Exactly. So thanks, Charles, for raising this, because I forgot to sort of highlight this point.
I think you are trying to represent something that's spatially very localized with waves, plane waves that cover the entire space. And so you rely on very subtle cancellations to actually generate these sharp gradients in physical space by superposing the Fourier mode. So you just get rid of a few and you get a completely different picture.
But that picture sort of goes away a little when you start doing it homogeneously. I agree with you more strongly when you're doing it in a scale invariant way. That's because you have a greater weight on the small scales, right? It's slightly hard to, it may still be true, but it's slightly hard to reconcile this when you pick up the same signals when you do it in a homogeneous way, right? You agree? And so there's a, there is a sort of theoretical block there to see. So just to finish, I think one really has to look at the triads, and we sort of use many estimates with Michele Buzzicotti, who's a grad student, he just graduated, to try and understand how one can recast this problem in terms of number of triads. In burgers, it's possible, but in the Navier-Stokes, it's a nightmare.
In fact, that same question I want to ask. So we need k equal to p plus q for interaction. If you just remove one of them, then you just block the energy transfers.
No. There are other channels for transfer. So the transfer doesn't
I don't want to see block all, but you're kind of, maybe the critical ones are being taken away.
So what you're thinking in terms of a percolation-like problem, but that doesn't show up here. So in a percolation problem, if you remove a critical number of bonds and your percolation stops, but because of the triadic nature here, you sort of circumvent that problem quite a bit. So, I mean, one of the problems to go, if you're doing it fractally, to go to low enough dimensions is the fact that you need more and more sort of time in terms of computational time to actually get non-equilibrium steady state. But there is still a finite flux.
So you can look at a single mode and check out how much energy.
That's right, from the left and right.
It has been checked out?
Yeah. And that's fine.
The net energy going out and coming in is zero at a given?
No, so in the 2D problem, where you know that there is this, where there is this strong prediction that we had about the critical dimension, there you do see the fact that the flux goes down, but that's for a different reason. And there's a vanishing flux,
little comment.
And that's sort of associated with a sort of diverging Kolmogorov constant.
So Frisch had done, Frisch and one more person, I think, the d-dimensional turbulence.
Right.
Is it connected with your d-dimensional or not? I mean,
so this was the last point that I was raising. So one of the problems with that, so Fournier and Frisch's calculations for closure, is the fact that if you start the, let's say, the EDQNM problem, and you go down in dimension, so below dimension 2, that problem is, you can't, it's not well posed. That's because the energy stops being positive definite, right? So there the critical dimension is 2.07 or something, and you can't go below 2. However, I didn't show the analytical stuff here. So using this sort of probabilistic argument on the EDQNM or closure model, you can now actually go to dimensions less than 2. And you do see the same features as from the Navier-Stokes DNS for the closure model. So it's, again, a way to write down closures in dimensions less than 2. Yes, so that again, and we never wrote it up, but so that circumvents the Fourier-Frisch problem.
Okay, I can see a strong similarity between what you are saying with quantum turbulence, as I tried to explain in the morning. Because there, if you just collect the data, and you have your particles which are passing quantized vortices, so each quantized vortex serves as a strong intermittent push for such a particle. So if I then filter the data, just the way as you explain here, I see exactly the same effect. So these tails which are there, they become smeared out, and you recover a parabolic profile. This is the same. So I suggest that if you put your time series through a time filter, then you should see the same effect.
But I don't know if that's true. I don't know.
I don't know whether it's true, but it's probably worth a try.
I'm happy if there's experimental data that's, Greg or you or someone, and we could sort of look at these masks on those data. But I really, I'm not going to hedge my bets and sort of say it one way or the other. Because the only thing that, I know, and that's from Luca's work, not mine, where he could see, something exactly of the sort that both of you are suggesting was done on the DNS data, post-factor filtering, and you see it's slightly delayed, but delayed in terms of the deficit dimension, but you do see.
What if my forcing was done on a fractal set of a dimension less than 3?
So here the forcing, of course, obeys the fractal nature of the Fourier space, right? Because these are all forced simulations, and you project, so these are non-equilibrium stations.
I want to force it not in, not space-filling way, but in a fractal way.
In physical space?
In physical space, yes.
Like in a, yeah.
Yeah, let's
Okay, I guess
Like with turbulence? No, I
just looked at Greg and I thought about it.
Okay, so we'll continue discussing this over the
I'm
next.
happy to conjecture, but I don't think we have.
So we'll continue debating this over the next few days.